So now let's enter into the world of C++. Now, before we enter into the world of C++, let's discuss a little bit of memory, because without understanding some principle of memory, um, the C++ can be a pretty daunting language. One of the reasons C++ is a language choice wherever you want to gain efficiency is that it offers the user a lot of control over how to manage the memory. So in C++ world, memory has to be managed fully by the user. And sometimes people hate that because in the Java, for example, there are garbage collectors who will take care of the memory management. But in C++, you have the power to manage the memory the way you like. And therefore, because of the presence of this memory management aspect, C++ is a fairly difficult language. And it's very rich. One can pretty much spend the whole semester just discussing C++. But what I would like to do here with the two sessions is that I would like to just give more whatever is needed for you to pick up C++ very quickly. And I would keep the introduction to that level. And at the same time, I'll give you some very in-depth points which you probably would not encounter if you just pick up a textbook, for example. All right. So as I said, in order to understand C++, which is a procedural language, you would need to understand some level of how the memory gets managed. So let's draw a rectangle. Think of this is your computer's memory. So typically, the computer's memory is divided into different sections. Okay. So this section is called the stack section. Then you have the heap section. And then you have a section called globals. And then you have sections for constants. And then you have the text section, or where the code goes, the assembly code. So this is where your compiled assembly goes. So when you are writing an entry function, let's say main, so int main, this is the most basic thing you can write, right, inside a C++ file. So you can simply say return 0, indicating that my program is ending gracefully. So inside this block, so this is a function. So inside a function, when you define a variable x, then this x goes to the stack. So anything that comes in between these two parentheses, in C++ you can have interspersed sort of definition. What I mean is that you can write here, let's say cin greater than x, which is basically I'm reading some value from the standard input or the input stream into the variable x. So this greater than, the way to see it is that it's almost like it is pointing to x. In other words, this is the direction in which the data is supposed to move. So from the input stream, the data is supposed to move into the variable x, and that is why it is greater than. So after writing that, you can introduce a variable y here. So in other words, the variable x, y, z, or whatever variables you want to define, they don't have to necessarily come in the beginning of the function. So they can be defined anywhere. But as soon as you have the variable defined locally, so this is a local definition, it goes into the stack. So you can see, so the variable is placed somewhere here, let's say. It's a memory, so somewhere the stack pointer is pointing here. That's why it goes here. So every variable is allocated. So it will be associated with some address where the variable is getting stored. So it will have 1, 2, 3, 4, something, something, you know. So this is the location where the value of X goes. And the stack grows downwards. And then when you have something which is dynamically allocated. So for example, if you write int star y equal to, now of course you are writing in some block here. So it's a local variable. So you write int star y equal to new int. If you write this, then what happens is that this y is now defined here. This y is essentially the pointer variable. But the memory that gets allocated, it gets allocated here. So in other words, this y, that variable, now this y variable, it's a pointer variable. So therefore it has to point to this allocated memory. So when you are just allocating this memory, it's not initialized automatically. So therefore it contains some garbage value here. So you would have to explicitly say star y equal to 5. Then the 5 goes here, and then you can say that y now points to this particular location in the heap which stores the value 5. So in this way, you need to have this picture in mind. So what you now can see is that the heap grows upward. So if suppose your program is written in a very poor manner and you exhaust this space, right? Because this is the boundary, then it will kind of go through a crash. That's when the program crashes. Okay, so this is first very basic understanding I wanted you to have. Now, of course, when you are defining any variable outside of the function, let's say int g, so that's a global variable, right? The global variable goes to this section. So there is a designated section where it goes. Okay. Any questions so far? All right. So now let's write.
Oh, wait, I have a quick question. Sorry, I put in the chat, but my question is, why is the specific directionality of how the stack and heap build important for us?
This is in terms of how the address is growing. Mm-hmm. Right? So address in this direction is sort of growing down. In this direction, it is growing up. That's where the directionality comes from. Is that clear?
So it's actually kind of designed behind the scenes, like the language, so that the direction matters. Like the heap builds upwards, the stack builds downwards.
Right. So this is how the operating system is managing this, right? This is not exactly the the way physically how things are going to be stored, because there will be a lot of layers that are being managed by the operating system, the memory hierarchy and so on and so forth. But this is the sort of, you can say, the virtual layer that is revealed. So in other words, when you are asking what is the address of X, right? Then it will return this value, right? Right? So this number that is allocated, it is allocated by the operating system. So this design of growing upward or downward, it is corresponding to the operating system. Is that clear?
Yeah, thank you.
Good. All right. So the typical mindset that you need to have when you are having a pointer, let's say a pointer a val, right, is equal to ampersand some val, right? So the idea is that here you have some val whose address is a val, right? So a val is pointing to this some val. Okay, so have this picture in mind. Now things become a little more complicated when you have arrays, right? So when you have arrays, so you can say int star a. Let's say we'll come to this later. So let's say you have int a 6. So when you have int a6, then what happens is that there is a contiguous chunk of memory that is dedicated for these elements, right? So this is going to be a0, a1, a2, so on and so forth, and you have a5, right? So these are the values, right? And the indices are, so this is the indices. These are the indices. So 0, 1, 2, dot, 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 5. So now you have defined this array, but interestingly, you can also refer to them through the pointer. So typically when you have defined an array, when you ask what is A then, right? So A is essentially the value of address of the first element. So here, so you can think of this is the address. So A, this is A plus 1, A plus 2, A plus 5. So this is your pointer. So can you tell me, how can you extract the value with A plus 1? If you want to extract A of 1, how would you extract the value with A plus 1? What would be the way to write? So what is A plus 1? So let's clarify this. What is A plus 1 here? A plus 1 is the address of A1, right? And therefore star, which is now you're dereferencing, so star A plus 1 is same as A of 1. So therefore this is another way of extracting the same same value. Okay. Any question on this point? Is this point clear?
Wait, so syntactically, would that work? Dereferencing A1 as star A+1 that would work in C++.
Right now, whatever I'm showing is syntactically valid.
Okay, okay. Thank you.
Whatever I'm showing, this I'm following very clearly the syntax of C or C++, you can say in this case. Okay. But I want you to understand conceptually what these things mean. So now, who can tell me when we are saying A+1, what does this +1 increment literally mean? So A is the location of A0. So when you're doing +1,
whatever is adding is the index of the array.
so what unit do you think it has to go forward?
In ones.
So it has to go forward the unit that is dependent on the type here. That's why the definition of this type is very important. Because if this is char A of 6, right? The char is stored in 1 byte, right? So when you're doing 1 plus 1, right? You're just incrementing by 1 byte. But when the type is int, +1 amounts to, depending on your machine, it can be 4 bytes or 8 bytes even. Does that make sense? So this one is context sensitive. It is dependent on what is the type of this. Okay. So now let's ask ourselves this question. What is the difference between if you define as int star a and int a, let's say 50? What is the difference between the two?
First is a pointer. The second is the you're just initializing an array, right?
Correct. So let's understand it very clearly, okay? So this essentially means that I have got an array A allocated for 50 elements, each of which is of type int. So now this is a pre-allocated, right? Here, if you do A equal to 25, let's say, do you think this is going to work?
No, because you already initialized it as a list, or rather an array instead of an integer.
It's not going to work. Here, this one is a pointer to an int. And the key point is that here, because it's a pointer, therefore, it can point to anything in due course of time. It depends on how you are programming. So right now it is pointing to an int, right? But this here, in this case, A can be changed at any time. So that's why I drew the picture here, right? So here, remember this Y was a pointer, right? So Y is pointing to this 5 based on this statement, star Y equal to 5. Sorry, not based on this, sorry. Y is pointing to this based on this. This is defining where it is going to point to. So this allocated this piece of memory and Y is pointing to that. So later on in your program, you can define again Y, let's say equal to an address of another variable B. So then it will start pointing to some other location. It could be in stack, it could be in heap, depending on where it is, because Y, by being a pointer, it can point to anywhere. And in your program, you are the one who is on the driver's seat to manage the memory, right? So it need not only point to this, it is very flexible. You can make it later on point to another location, for example. So I want you to have this clarity. Now, once you have defined or allocated the memory, it's now your responsibility to make sure that this allocated memory is freed up. So freeing this is your responsibility. Okay, it's very important, because if you don't free, what's going to happen? You just keep on adding sections here, right? And then you are no longer accessing, but this section becomes unusable. So when you create too many unusable sections in the memory, that is what is called memory leak. And if you keep creating these without actually taking care of freeing up, at some point in time, it will hit here. And therefore, your program can crash after some time. So it is very important for us to always leave things in a clean state. And that is done by simply calling delete. So you have to call delete on Y. So now if here you have defined this as element, let's say of size 50, right? Then you have defined 50 such contiguous locations. You have allocated space for that. Then here, syntactically, you will have to put a bracket here when you're freeing up that memory. So and delete, they go in pairs. So in C world, there used to be malloc and free. They are not interchangeable with new and delete. You cannot just do a new and then try to free up using the free syntax. So that's a very important thing to note if you are used to writing C code. Any questions so far? All right, moving on.
Professor, sorry, you mentioned that you can reassign a pointer to any other object after you've initialized it.
Yes.
For a point to an integer, you can't then initialize that or reassign that to, say, a char or something like that, right?
What is the definition of this? This is pointed to an int.
Right. Okay.
It is not just a pointer. That's why we have to understand the definition fully.
Thank you.
All right.
I'm sorry, I have another question. So you said that heap is allocated from bottom to top. So after like you used up one of the memories and you freed it, the next the new allocation will automatically happen on the previous position, or it's gonna allocate somewhere up it.
So what is going to be the effect of, let's say, delete calling on Y if the Y is pointing to this location? It's literally has the effect of this. Oh, come on. It has the effect of this. I erased too much. Let's see. Yeah, but you see. So when it is really freed up, then that space is open, right? Now, whether the next allocation is exactly going to happen here or not, that is completely dependent on the operating system. Right? It can, wherever the first allocation point is, that's where it's going to allocate. But the point is that that space becomes freed up for allocation.
Thank you.
Clear? Okay.
Yeah, thank you.
All right. Oh my God.
I have another question
Go ahead.
about it. So when you free up the memory, like the address to the heap,
Yeah.
does Y still stay there? Like Y is still in the stack memory.
In the stack memory, it's in a different section.
Okay.
So when does the question to ask is that when does Y get reclaimed? When you come to the end of the function. So all the local variables, they are gone. So the existence of these variables in the stack is within this region, right? That's the life of these variables, local variables.
Wait, and then another question.
Yeah.
Just to clarify. So if we make like another function, right? below main. The activation record is also opened in the stack, right? Until when the function closes and the activation record also closes. Is that correct?
So activation record comes into picture when you're actually calling the function. Just by defining the function, that doesn't bring activation record into the picture, right? There has to be real activation, which is happening through making a call to that function.
Yeah, but so when you call the function, right? So,
so
the activation record is opened, but then when you, for example, return out of that function, then that activation record also closes.
Yes. So let's see this how this happens is that when you are in a particular function, right? So this is your stack frame for this function, right? So when you activated the function, right, it creates the stack frame for another function, which is called, right? And the stack memory is managed here, right? And when it comes to the, when that comes to the end, the stack pointer goes back here, right? Here or here, whatever, wherever the end of the stack frame is. In other words, when the function is called, the return address is kind of stored, just so that you can come back to the place where you can start allocating the memory corresponding to the current function where your execution point is. Is that clear?
Yeah, so there's always basically a stack pointer to remember it for main, so that whenever you want to go back to main, the stack pointer knows where to go, basically.
Exactly. It's
okay,
managed
thank
by
you.
the compiler. It's managed by the compiler. So this function we call function 2, right? Right. So if you are inside the function 2, right? This is where you're executing, right? Then your activation record will be here, right? And the stack pointer will be pointing here. And you are, as you're executing, you may encounter int y here, right? And therefore, accordingly, this y will belong to the stack frame corresponding to function 2. And all of these, like the sequence in which the stack frames get managed is all encoded inside the assembly code that gets generated by the compiler. So once the program is compiled, all the management of the stack frames are integral part of the generated assembly code. And that is why you have in the program memory this text section, right? This text section is referring to all these memory, which it is utilizing as the program is executing. All right. I can speak about this because my area of expertise is really compilers. That's the area in which I have specialized in. And therefore I can talk as much as you like in the area of compilers.